confidence level. Let's say, what do we have here? Now you see here we have group statistic. It says that the mean value, the total number of samples in 45-mile category is 34, mean speed is 48.41, and on 35-mile per hour speed limit roadways there were 30 values that I collected, and the mean speed is this. Now see here, we have equal variances assumed and we have equal variances not assumed. So which one to pick? I wrote it down somewhere. So if the significance level like this 0.251, if the significance of these Levene's test is less than 0.05, then use this value. In our case, this significance level of Levene's test is greater than 0.05 or our significance level, then we will use the results of this equal variances assumed, which means that we are assuming that the variances in the two different data sets or in these two different categories are same. So now we have degrees of freedom, we have t-statistics computed, here the p-value is, or the significance value is 0.0. Now this 0.0 is less than our significance level of 0.05. Correct? This p-value 0 is less than our significance value of 0.05. So we reject our null hypothesis that there is no difference between the means of the vehicle speeds collected on two different roadways. Understood? How did we interpret the results? This 0, this p-value is less than our significance level of 0.05. Our assumption was that the mean speed of the vehicles collected on 45-mile per hour roadway and the mean speed of the vehicles collected on 35-mile per hour roadway are equal. Our significance value over here, which is 0, is less than our this p-value is less than our significance value of 0.05. Therefore, we reject the null hypothesis that these two mean speeds are equal. They are not equal. Let's conduct one more test and see what results do we get. Let's change our... Yes, because that's a very good question. The degrees of freedoms are different because the way when we have all the numbers that I showed you was for one sample t-test, just for the one variable. When you are comparing the two different samples, then the equation is totally different. So therefore, the way degrees of freedom are computed are different as well. So the equation that I showed you was for the data set that we it had just one variable of which was height. So it's simple. So degree of freedom is simple. It's total number of points minus 1. However, when we are conducting such tests where we are comparing the groups, or we are doing some other, like we are comparing two different variables, or we are comparing the mean inside one variable, then the way degree of freedom is computed is different. The equation is different. It's more complicated, and that's why you see the different numbers here. Clear? Is it clear, Mudassar? No? Okay. See, okay, let me try. This was one sample statistics, correct? I don't have that equation here, but what I'll do is I'll show you that equation next time. I don't have it right now. Those equations are complicated, where the sample sizes are from the both variables are considered, from the both groups are considered, the standard deviations from the both groups are considered, and then the degree of freedom is computed. And then even the t-statistics, the way t-statistics is computed is also different. So the degree of freedoms are different. So now in this case, we had just one, this is one sample statistics. This is based on the equation that I showed you. That's why we have n-1. Over here it's more complicated. Okay. Now let's do this example once again, and let's change here and see if there is any difference between 40 and 35. And let's change our confidence level to 99% and see what happens. Now you see that the mean values, these are the mean values under each group. And since the significance level, this of Levine's test is greater than, the significance value of Levine's test is greater than 0.05, so we'll stick with equal variances assumed. And we'll consider the significance or the p-value here. Now again, the p-value of 0.0 is less than our significance level of 0.01. So we reject the null hypothesis that the speeds under these two categories are same. The speeds under these two categories are not same. So our null hypothesis is rejected in favor of the alternative hypothesis. Clear? Okay. And then paired sample t-test. Now what is paired sample t-test? What is usually happen, what the way we do it, or the usual where we apply is that there is a roadway and we go and we find out the speeds of the vehicle, or we collect the samples for the delays So for one cycle the delay was 60 seconds, the second signal cycle the delay was 30 seconds. These are we collect some data, then we come back in our offices, we try to do some improvements, whether it's in terms of the signal timings or whatever. We implement those improvements on that roadway, we go back and we collect the data on the same roadway. Then to see whether the improvements are really effective, have they made any effect, we conduct the paired t-test, which means comparing. This is like kind of before and after. So you collect one thing, like the before and after. So you collected some data, then you went back, you did some improvement, and then you went again and you collected the data, and now you're comparing that it was your whatever treatment did you do, was it effective or not. So that is the paired variable. That is one example. The other example is, it could be that you select two different groups, and then let's say we selected two different groups of students. One group, we treated them, we taught them some techniques of conducting a test or writing a test, or like we gave them some hints, some tips, we trained them. The other groups, we did not treat them. Then I think this is not a good example. This might not be a good example. But usually the paired variables or paired t-tests are conducted when we do the before and after studies. So that what we want to do is we want to see how effective our test was. So we apply the test on the same group of people. Okay, so the way I'll reword my example. So we selected a group of students and we asked them to take a test. They took a test, and then all of them got certain scores. We found out the mean of those scores. Then we trained that group of students, and then after the training we asked them again to take the test, and then we computed the mean value of that test. Now we see whether the training did it make any effect on them. If it did or not, we compare the two means and see if the p-value or is less than or greater than significance level, then we accept or reject the hypothesis. So here let's assume that speed data, this first variable, is our variable number 1, and posted speed limit is our variable number 2. So let's assume that this was the speeds of the vehicle before we made any improvement on the roadways, and this was the speed of the vehicle after we made any improvement. So let's see Did our methodology, did our treatment had any effect? Again, the option is 95%. Continue, we do okay, and let's see what we have here. So here we see that the speed data and posted speed limit, it's considered as 1. And then we come here and the mean difference, the difference between the two means is 3.975. The standard deviation is this. And then the significance value is 0.0. So the significance value of, and our claim was that, and our null hypothesis is that there is no change, there is no improvement. That was our null hypothesis. Before and after, there is no improvement. Now this significance value of 0 is less than this p-value is less than our significance value of 0.05. So we reject our null hypothesis in favor of the alternative hypothesis. Our null hypothesis is that there is no improvement, there is no change in speed. Even though we did an improvement, we don't see any. However, our tests show here that there is a significant difference in mean, which means whatever improvements we made were effective. So we reject based on this value of 0.0, which is less than our significance level or value of 0.05. We reject our null hypothesis, and our alternative hypothesis, which we accept, it says that there is a significant difference in the mean speed, or our improvement techniques worked. They brought some improvement in the speeds. Let's see if we can do this pair t-test again based on some other variable. Actually, you know what? This pair t-test is done on the same type of data set. Now, I cannot compare lane width with the segment length, like the distance between the signals, because these are two different. It's like comparing apples and oranges. So we always either compare apples or we compare oranges. We don't, in paired sample t-test, we don't compare apples and oranges. So these are three different types of t-tests that we usually conduct. The compare means is, let's see what does it do. Dependent list is, and independent list is, let's say, posted speed limit. Let's see what happens here. So what it does, it just gives us a chart here with the mean value. So within this group of 35 miles per hour, our mean speed is 39. Within this group, the mean speed is this. Within this group is this. It's just comparing the mean. It's just showing what our mean values are, and then the sample size here and the standard deviation here. So we can compare the mean and see how much different they are. We can conduct one sample t-test when we have just one variable and we have certain claim and we want to see whether that claim is correct or not. Independent sample t-test is the one which we do when we want to compare. So the variable remains same, meaning we want to compare the means for the same variable, however, for different categories. So we had different categories of roadways and we wanted to see whether the speeds of the vehicles on these different roadways, are they significantly different or they are not significantly different. That is how we compare the independent sample t-test. And paired sample t-test is actually the before and after, usually, that we conduct a test, we do any improvement, and then we conduct the test again, and then we compare the mean to see whether whatever improvements we implemented were they effective or not. One-way Anova is actually one-way Anova stands for analysis of variance. This is usually we do when we want to compare the means of an independent variable which are affected by a categorical variable. So if, for example, if I have categorical variable good, bad, better, and I have an independent variables between, let's say, the level of like sugar level or something like that, and then